Really? That's the way that oh, really?
Good morning, everyone.
Morning.
Let's continue working on chapter 2, where we are going through the general steps of the finite element for a simple spring element. And we started this week by looking at a spring element. Thank you. Spring element, we defined a 2-node spring element, 1 and 2, that has a spring constant of K, oriented along the x-axis. And we were able to derive the element stiffness matrix as K minus K minus K and K for the spring element. We looked at an assemblage
Is it a review? Okay.
of 2 spring elements. Where this was K1, extends between node 1 and 2, connected to another spring element that has a spring constant K2 and extends from 2 to 3. We were able to write the structure stiffness matrix K, and we did put it together, and we looked at a K1 minus K1 minus K1 and a K1. And then we superimposed the element stiffness matrix for element 2. So we started seeing the K2, the minus K2, the minus K2, and the K2. And for the elements that do not have contributions, we simply added zeros. And we said this is corresponding to degrees of freedom 1, 2, and 3. And also we related the columns to 1, 2, and 3. I want to remind you that when I write my global stiffness equations described as F equal to K multiplied by D, we do not have a solution until we apply boundary condition. So K is a singular matrix. We cannot solve unless we apply boundary conditions. And this is the topic for today. So today we're going to learn about boundary conditions, how to apply them and solve the equations. So boundary conditions must be applied to global equations to be solved. The structure system is unstable without boundary conditions. The structure system is free to move as a rigid body. Without boundary conditions. The number of boundary conditions necessary is equal to the number of possible rigid body modes. Types of boundary conditions. We have two types: homogeneous boundary conditions and non-homogeneous boundary conditions. The homogeneous, these are the most common. And occur at locations that are completely prevented from moving. That is, the degree of freedom is equal to 0. Degree of freedom equal to 0. When I say degree of freedom here, I'm referencing displacement or rotation, right? So translational or rotational degree of freedom. On the other hand, the non-homogeneous boundary conditions would occur where a non-zero or a finite value of displacements are specified. Finite value of displacements are specified. So if it is non-zero, there is a finite value. Is it too small? Would you like me to zoom in? Sorry. that better? Usually when I have a specified value, this could be as in settlement of support or prescribed displacements.
Would that be for like something that's like a rubber or something that's moving to?
It doesn't have to be a rubber. Sometimes, for example, there is a clearance between the supports and the element, and you know how much when this is loading is expected to go. Right. So let's look at applying homogeneous boundary conditions. And I think one of the best way to look at it is to take an example. So let's look at this assemblage of the two springs that we worked on. So we still have 1, 2, 3, K1 and K2. And now I'm gonna make or apply a fixed support at node 1. So node 1 is fixed. That is U1 is equal to 0. Now remember, we had our system relations, K1 minus K1 minus K1, K1, and then we had the plus K2 minus K2 minus K2, K2. We had the zeros. We had this multiplied by U1, U2, and U3 is equal to F1, F2, and F3. So these are the system equations. Now we learned that they have no solution until we apply the boundary conditions. So now if I apply the boundary conditions, I would simply make this U1 equal to 0, right? So if I do here U1 equal to 0, K1 minus K1, 0, minus K1, K1 plus K2 minus K2, 0, minus K2 and a K2, multiplied by a 0, a U2 and a U1 is equal to F1, F2, and F3. Now, if I'm trying to solve this system of equations, now clearly the first row here, the unknown is not a displacement, but could be the support reaction F1. So I can say I'm gonna get the first row out of my system, and also the first column is multiplied by 0. So I can delete the row and column corresponding to the homogeneous boundary condition degree of freedom. So I can come here and say, I'm going to delete this row and this column. So we are going to delete. Yes.
Does it mean you have a system where you fix at both ends, then you may end up having two homogeneous conditions So are you at liberty to start anywhere or you must start from?
No, we can actually delete 2 rows and 2 columns in this case, and we're going to be left with 1 equation.
Okay.
Yeah. Okay. So we are going to delete the row and column corresponding to the 0 displacement degree of freedom. I'll be using DOF for degree of freedom, okay? Now we can start solving for the unknown in an easier way, because this would reduce my system to a K1 plus K2 minus a K2 minus a K2 and a K2 multiplied by U2 and U1 equal to F2 and F3. And F2 and F3 are knowns. So now we can solve for the unknown displacements. Here would be U2, sorry, this is a 3. I'm sorry. Oops, sorry. So I had here a typo. That's a 3 and this is a 3. U2 and U3. We're good. How about applying non-homogeneous boundary conditions? So again, I'm going to be looking at my assemblage of these 2 springs. Oriented along X, node 1, 2, 3, K1 and K2. And I may have here an F2 and here an F3. And at node 1, I have a prescribed displacement. So I know this delta. So U1 is equal to a delta. So when I write my equations, I have this K1 minus K1, 0, minus K1, K1 plus K2, K2, 0, minus K2, and a K2. Now these are multiplied by, at node 1, I have a delta. Then I have the unknowns U2 and U3. This is equal to an unknown force F1 and 2 known forces F2 and F3. Now we are going to consider only the second and third rows. But we want to be careful here. If I want to consider the second and third rows, I have to take into consideration that if I go to the second row, the first element is multiplied by a delta.
You didn't write K2 negative, is it? Or is it?
I missed the negative here. You guys are paying attention. Good. I like that. All right. So now if we consider only the second and third row, we cannot delete row 1 and column 1 like we did earlier as for homogeneous boundary conditions. However, we must transform the terms that are associated with the known displacements so displacement or displacements in this case is going to be U1 to the force matrix. To solve for unknown displacements. Okay, what does that mean? I'm going to look at if this is 1, 2, and 3, we're going to look at row 2 and row 3. And I'm going to come here, and if I am to write the equations, I'm going to have a minus K1 delta, and that's a known quantity, right? Plus a K1 plus K2 multiplied by U2 minus a K2 U3 equal to F2. That's my second row. My third row is going to be a 0, just happened to be a 0 times delta plus a minus K2 U2 plus a K2 U3 equal to F3. Now, in order to solve for these equations, I'm going to move these first known terms to the right side. So I'm going to write it as K1 plus K2 times U2 minus K2 U3 is equal to F2. And I'm going to subtract the minus K1 times delta.
So can we say this is similar to the question in
So on the third row, I'm going to be looking at a minus K2 U2 plus K2 U3 equal to F3. In matrix form, I can still write that as a K1 plus K2 minus K2 minus K2 K2 multiplied by U2 and U3. And I will say this is equal to F2. And I am subtracting the element that corresponds to first degree of freedom in row 2 times the known degree of freedom delta. So minus a minus K1 delta and the minus inside the bracket here is coming from this minus. So I'm not adding that. So I'm just subtracting the element 2, 1 times this degree of freedom. And here I have F3 minus 0, just happened to be 0. Now we can solve for U2, and U3.
K1 plus K2, okay.
In general, if I have this K multiplied by U equals to F, where we can partition this K. So like after applying the boundary condition, rearrange such that we end up with a partitioned matrix of K11 here, K12, K21, and a K22, multiplied by a displacement matrix. Sorry. A displacement matrix D1 and D2 is equal to this F1 and F2, where D1 are the unknown displacements that we're trying to solve for. D2 are the known or prescribed displacements, known. And again, these are typically non-zero, right? Known displacements. F1 are the known forces where we have unknown displacements. And F2 are the unknown forces. If we can rearrange to such an order, then we can look at the first set and say we have K11 multiplied by D1 plus a K12 times D2. D2 is the known displacement, is equal to F1. And F1 are known forces. So these are the only unknowns. So in a way, we are simplifying this system of equations. And then we can move K12 to the right side. So we can get K12 times D2. I'm sorry. This is K11 times D1. And I'm going to move this to the other side, is equal to F1 minus K12 times D2. Here, I have a system of equations that is reduced compared to the first one. And where I have a solution, I can get a solution for D1. So solve for D1. Once I have D1, I can next come and write K21 times D1, which is known now, plus K22 times D2, which is known, is equal to F2. So here we also solve for this F2. Which is, by the way, this is what we did for the spring assemblage. So this is a more generic form. Let's take an example of mixed boundary conditions. So now we are going to be looking at an assemblage of 4 springs. So we have 1, 2, 3, and 4. So we have 4 elements. Each of the elements have a spring constant K. The nodes are 1, 2, 3, 4, and 5. We have a fixed support at 1, and we have a prescribed displacement at 5. This is equal to delta. K is given as 200 kilonewton per meter, and delta is equal as 20 millimeters. So you can think about it as having this assemblage fixed at the left side, and I'm simply pulling it. I don't know the force that I'm using, but I'm pulling it such that I am elongating the system by a distance delta of 20 millimeters, right? We want to find A, the global stiffness matrix, B, the unknown displacements, C, the global nodal forces, and D, the element forces. That's a nice numerical example here. Okay, now when I say global nodal forces, where am I gonna get these forces? Clearly, there is nothing applied to 2, 3, and 4.
Internal forces.
Yeah, but I'm talking about global, right? So there are no external forces. So now I'm looking at these global nodal forces. I'm expecting an F1 and an F5, right? When I say unknown displacements, this is known, but the unknown will be U2, U3, U4. U5 is known, right?
So, by implication, if the forces are not clearly stated out, then we shouldn't assume there are forces at the nodes. We shouldn't assume if they're not stated.
No external forces. If there are external, they need to be given, okay? But we're solving for the internal, right? Okay. And I will take the opportunity of this example to demonstrate how I apply what we learned to solve these problems longhand, right? So the first step I'm going to do is to write the element stiffness matrices for each of these elements, right? Which is easy because they all have the same K. So, but I'm going to go through the sequence so you can follow the steps. So number one here, we're going to do the element stiffness matrices. So I'm going to have a K1 for element 1 that is going to be equal to a K1 minus K1 minus K1 and a K1. And if we're going to use the direct method, we want to label the rows and columns to their corresponding degrees of freedom. Okay, and I'm going to use green for that. So for element 1, it extends between node 1 and node 2, or degree of freedom 1 and degree of freedom 2. So I can come here and say, well, the first row would correspond to 1, second to 2, and same here. So for each element, we're going to do the same. So now for 2, I have again K1, K, actually it is the same K, so I shouldn't really write a subscript. I'm going to just call it a K. Sorry for that. So there is no need for the 1. Now element 2 extends between node 2 and 3, or will correspond to degrees of freedom 2 and 3. For 3, we have the K, the minus K, the minus K, and K. We're going to label 3 extends between 3 and 4. So degree of freedom 3 and 4, 3 and 4. And finally, K for 4. K minus K minus K and K. And it extends from 4 to 5. So I'm going to go from 4 to 5, 4 to 5. And we want to apply the direct stiffness method to assemble K. So we're going to use the direct stiffness method to assemble the global stiffness matrix K. Okay, so now one thing I need to ask myself, what is the order of the global stiffness matrix K? 5 by 5. Okay. So when I want to do that, I want to write here K, this 5 by 5, and I'm going to go 1, 2, 3, 4, 5. So we're going to have 5 rows and 5 columns. I go here like 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And I'll be looking for the elements from the element stiffness matrices. So I'm just going to be copying. So I come here and I'm going to go element by element. So for first element, it goes here, K1 minus K1 minus K1 and a K1. Right? Okay. For element 2, I have here a plus. Oh, there is no one. Sorry, I keep doing this mistake. So plus K minus K minus K and a plus K. You see here, it's all at 2 and 3. So like for element 1, this is where it went. For element 2, it came here. Right? And then I keep going. For element 3, I'm going 3 and 4. So I come here and do a plus K, a minus K, a minus K, and a K. So it came here. And then element 4, degrees of freedom 4 and 5. So I got a plus, a K, a minus K, a minus K, and a K. So this here comes 5. Everywhere that I don't have any elements, I fill in with zeros. So we're going to put a bunch of zeros. 0, 0, 0, 0, 0, 0. And it's symmetric. Right? So we added 10 zeros. So this is how we use the direct stiffness method to assemble this. Now, numerically, I'm going to substitute using the 200 for K. So I have here K is equal to and I go like 200 minus 200, 0, 0, and 0, minus 200. I have 200 plus 200, that's a 400, a minus 200, a 0 and a 0, 0 minus 200, then a 400, a minus 200, then a 0, row 4, a 0 and a 0 and a minus 200, a plus 400, and a minus 200, and row 5, 0, 0, 0, then a minus 200 and a 200. So this is the global stiffness matrix, part A. Next, we go to part B, which is finding the unknown displacements. So now, because U1 is equal to 0, so we can delete row 1 and column 1. Now U5 is equal to delta is equal to 20 millimeter. So eventually we are going to remove row 5. So let me start first by the first step. So the first step here, we are gonna delete row 1. So I'm gonna start from minus 200, 400. Oh, I did a mistake here because I need to delete also the column. So in a way, we are deleting this and this. So I should start with a 400. a minus 200, 0 and 0, then minus 200, 400, minus 200 and a 0, and then I have a 0, minus 200, 400 and a minus 200, and finally a 0, 0, minus 200 and a 200. Oops. These are multiplied by U2, U3, U4, and U5 is delta. These are equal to, we know that F2 is a 0, F3 is a 0, and F4 is a 0, but F5 is unknown. Now I want to remove row 5. So in order to remove row 5, I'm going to take the 5 column, multiply it by delta, and subtract it from the F. So we're going to go here 400 minus 200, 0, minus 200, 400, minus 200, 0, minus 200, and a 400, multiply by the unknowns U2, U3, and U4 is equal to, I have my zeros, and then I'm going to subtract the entries of column 5 multiplied by delta. So I get here 0 times delta, right? I have here 0 times delta, and I have here a minus 200 times delta, which is equal to 0, 0, and minus minus is a plus. So 200 delta. Right? Here so far? We can solve these 3 equations for 3 unknowns to find U2, U3, and U4. And we'll find here that the answer would be 1/4, 1/2, and 3/4 of delta. So it's kind of like saying, in order to get a full delta here, I will get 0, I will get a 1/4, I will get a 1/2. Did I miss something? Yeah, I got 3/4, then I get a delta. They are springs in series, and they all have the same stiffness. And of course, U1 is a 0 and U5 is a full delta. Numerically, I can write it all down. Because we know delta was 20 millimeters. So I get here 20. I get here 15. I get 10, get a 5, and I get a 0. So you see how gradually we are recording this space.
Okay, I'm actually sorry, I didn't understand how you arrive at this quarters.
This one here?
Yeah.
I just solved.
The quarters 1/4, 1/2. That's for the delta.
Correct. You look at these equations, they're in terms of delta. I have zeros and 200 delta,
Okay.
right?
Yeah.
So I'm solving for 3 unknowns.
Okay.
You can find the inverse of the matrix and you can multiply it to solve for deltas. Or you can just do it by elimination. Right? Okay. So this was part B. Part C is to find the global nodal forces. These are the Fs. So now remember, we deleted the first row. Now I can go back to the first row to find F1. So use row 1. I will get a 200 times, let me write it down. F1 is equal to 200 U1 minus 200 U2. Right? And then I have a bunch of zeros here. Sorry. So you see, this is row 1. So I have 200 U1 minus 200 U2, which is equal to 200 times 0 minus 200 times U2, which is 5. I get a minus 1,000 Newton. Now F2 is the same as F3, same as F4, is equal to 0. For F5, we use row 5. And we get F5 is equal to. If we look here at row 5, I have 3 zeros, and then I have a minus 200 and 200. So we get here a minus 200 U4 plus a 200 U5, which is equal to minus 200 U4 is 15 plus 200 U5 is 20. When I do the math, this is equal to plus 1,000 Newton. Which is, I have here a minus 1,000 pulling back, and here I need a 1,000 to pull me to the right, which makes sense.
So, but in real sense, assuming the spring is in real life, or maybe in a real life situation, assuming the spring is fixed at those points, does it mean the force applies through without being maybe losing in value? Maybe the 200 applies through without losing in value.
No, you can think about it much simpler than that. You can think about it. It is really stretched. There is a force applied such that I will stop applying the force when I hit a delta of 20 millimeters. Okay. And sometimes we do something like this in the lab when we're doing like tension tests. We go by incremental displacements, not incremental forces.
So the delta is like your guiding point, or maybe your
Correct.
limit. Okay.
Yes. You got it? Yeah. So I don't know how much. My question is, how much force does it take to pull it 20 millimeter? And the answer would be 1,000 Newton. Okay. So we can come here and write F1, F2, F3, F4, and F5 as equal to minus 1, 0, 0, 0, and 1. And I'm going to put it as kilonewton. Right. Sorry, I didn't put the units here. These were millimeters. So displacements are in millimeters, and global nodal forces are in kilonewton. Right. And finally, the element forces. So part D is to do the element forces. Now, when we are looking for element forces, we want to use the element equations, which is to remind you, we want to use this lowercase f is equal to this lowercase k multiplied by the corresponding displacement matrix. So for element 1,
So which we have already stated earlier.
we wrote the stiffness matrix earlier, right? So I'm going to use that. Very good, right? So I'm going to use here, I'm going to find F1 element 1 and F2 element 1. These are equal to what we wrote earlier as a k minus k minus k and a k. But now I have the element displacements, which we found to be a 0 and a 5. So when I do the math here, I'll find that these are going to be equal to a -1 and a 1 kilonewton. What does that mean? If I look at this very first element, extends between 1 and 2, this is element 1. At node 1, if this is the x direction, I have a force applied here in the negative direction of 1 kilonewton, and I have a force applied here of 1 kilonewton. So the element is in tension, and the internal forces are 1 kilonewton. Is that what we expect? What do you expect for all the other springs? Same, right? Okay, let's see if the numbers are going to work out. So like I go for element 2. I'm going to have here F2, 2 and F3, 2 equal to a k, a minus k, and a minus k, and a k. And now I have a 5 and a 10. And indeed, when I do the math, I'm going to get a -1 and a 1 kilonewton. Similarly, element 3, I'm going to get an F3, 3 and an F4, 3 that is equal to a k, a minus k, a minus k, and a k, and now multiply by 10 and 15. And likewise, we're going to get a -1 and a 1 kilonewton. And finally, for element 4, we're going to get F4, 4 and F5 element 4 is equal to a k, a minus k, minus k, and a k, multiply by 15 and 20. And also the answer is a -1 and a 1 kilonewton. Which does make sense and does meet our expectations. So this was a nice example where we applied what we learned on writing element stiffness matrices using the direct stiffness method to assemble the global stiffness matrix, applying both homogeneous and non-homogeneous boundary conditions to global system of equations that help us reduce a 5 by 5 to a 3 by 3 and we were able to solve for the unknown displacements. We used the displacements to solve for the unknown global forces, and then we use the displacements, global displacements, which can be related to the element nodal displacements. In this case, they are the same because the local directions are the same as the global, and used element stiffness equations to find element forces. So this example kind of put everything we learned so far in the process or the steps of the finite element method to solve a simple problem. There are three different methods for deriving element stiffness equations. We learned the direct one based on equilibrium for a spring, which works fine. But as we use more involved elements, that is not going to work. And we are going to need to use the two other methods, which are the variational methods and like weighted residual method. I want to start on using the variational method, specifically the energy method, to derive the element stiffness matrix for a spring. But given that we only have 10 minutes left, I think I'm going to save that for next week and push homework 1, because in homework 1, you have one problem on using energy method. So I'm going to give you more time for homework 1, but please complete problem 1 and 3 because they're not energy method. So the only thing that is left for us for chapter 2 is using the energy method or the minimum potential energy approach that we are going to learn when we come back on Tuesday. Okay, have a good weekend, and I'll see you all on Tuesday. Thank you.